This particular question is asking us to identify hydrogen bonding interactions between molecules. And it's specifically asking us to look for two different things. First of all, whether the molecule is able to form hydrogen bonds between molecules of the same compound. And it is also asking us whether the molecule in question can form hydrogen bonds between that compound and water, for instance, if it's an aqueous environment. So first of all, we should probably recall what our definition of a hydrogen bonding interaction is. So remember, hydrogen bonding is a type of extra strong dipole-dipole interaction. So remember, dipole-dipole interaction is between a permanent dipole, where when you see in the Lewis structure there is a difference in electronegativity between two atoms forming a bond, and it can interact with the dipole on an adjacent molecule. Okay, so the particular strong type of dipole-dipole interactions are involved with hydrogen bonding, which of course is not a real bond per se, but extra strong dipole-dipole interaction, so a kind of intermolecular force, is when we have a bond between oxygen hydrogen, nitrogen hydrogen, or fluorine hydrogen, because these bonds are extremely polar. Oxygen, nitrogen, fluorine are very electronegative. Hydrogen's more electropositive, so at the oxygen, nitrogen, or fluorine end is where you have your delta minus end of the bond, and at the hydrogen end of the bond will be your delta plus end of that dipole. And these are very strong. So in the particular case of a hydrogen bond, these are able to interact on a neighboring molecule with a very electronegative atom, which, as you guessed, it would be oxygen, nitrogen, or fluorine, which will have at least one lone pair associated with it. And of course, you can mix or match. You don't have to have an OH bond interacting with electronegative oxygen on a neighboring atom, but it could be one of either of them. Okay, so that is the kind of interaction we are looking at, because then you'll get this very strong, about 10% of the strength of an actual bond interaction between that delta positive hydrogen and the neighboring electronegative atom. So for some of these, we already have our Lewis structure, which is convenient. So if we look at the methanol first, you'll see that we have an oxygen bonded to a hydrogen. So we have a polar bond right there, okay? So again, the oxygen end would be the delta minus end, and the hydrogen end will be the delta plus end. Now, in this particular example, we should be able to imagine that if we had more than one methanol molecule next to each other, that well, they would both have a OH bond. So we could see that hydrogen bonding interaction between neighboring molecules. Okay, so if I just draw this like the opposite way around, it's going to be more fun to do than I initially anticipated. So then we obviously have our hydrogen, hydrogen, hydrogen around our carbon, like so, a little bit like this. So we can see that we would have that hydrogen bonding interaction there between this delta minus and the delta plus of this hydrogen on the neighboring methanol molecule. So we can be pretty confident that between methanol molecules, we would see a hydrogen bonding interaction. Let's get rid of all this stuff in the way. So we can say, yes, between the molecules of the compound, we should have a hydrogen bonding interaction. Okay, so to consider the effect with water, well, I guess we should remind ourselves what the water molecule looks like. So a quick reminder of drawing Lewis structures, right? You add up the total number of valence electrons. So for H2O, each hydrogen has one valence electron, and oxygen has 6 valence electrons, so that gives a total of 8 valence electrons altogether. You'd put oxygen as the central atom because it has the highest bonding capacity. If it's got 6 valence electrons around it, it's going to want to form up to 2 bonds, right? So you probably remember putting electrons as dots around. Hang on. And they only pair up when they have to. So we've got a pair on that side, and then a pair on that side, and then single electrons opposite each other to minimize repulsion. So we've got 2 spots where the oxygen is going to want to share electrons and bond. So each hydrogen has 1 electron, like so. So that is where we're going to see the bonds forming with oxygen, like so. So it's going to form 2 oxygen-hydrogen bonds and have 2 lone pairs left over. So how we would draw that would be using VSEPR theory. It's a steric number of 4, so a tetrahedral electron geometry. So it's actually going to look bent overall, right? So a little something like this, if I can try and make it look pretty. It won't look that pretty, but near enough to pretty will do for our purposes. So what we can see is that we very clearly have a polar molecule. The lone pairs on the oxygen actually go in the same direction as our bond dipole, which is convenient. So our delta minus end is where the oxygen atom is, plus those 2 lone pairs, and each of the hydrogens is a delta plus. So if we then imagine how that is going to interact with our OH bond on our methanol, we should be pretty happy that one of those delta plus hydrogens is going to interact. I'm going to do it a little bit like this, I guess. I'll get fancy with my keyboard here. Oh, that key's stuck. That's going to be disastrous later. Who would have thought I had a sticky key? Okay, so then we can see that hydrogen bonding interaction between the delta minus on the oxygen in the methanol and the delta plus from the hydrogen on the neighboring water molecule. So that can very happily have hydrogen bonding between molecules of methanol and molecules of water. Okay, so dichloromethane, oh, it didn't draw the Lewis structure for us, so I guess we're going to have to go fish. So CH2Cl2, great time to practice your Lewis structures. So carbon has got 4 valence electrons, each hydrogen has got 1 valence electron, and each chlorine, oh, need a bracket, has got 7 valence electrons. So that's going to give you a total of 20 valence electrons. Carbon is going to have the highest bonding capacity, right? Because it has got 4 valence electrons, like so, sitting around it. So each of those is going to want to pair up. So that is why carbon chemistry is so complex and fun, and carbon forms so many bonds. It likes to form up to 4 bonds, okay? So in the spirit of being like symmetrical, I would put the hydrogens bonding one each side like so. That sticky key is going to really frustrate me. No, it's not going to work. Okay. Never mind. Never mind, sticky key. I'll have to draw you in later. And then my chlorines will go either side of this. I like to draw it nice and symmetrical because, you know, solid state chemist, I like symmetry. What can I say? So, are any of these bonds polar? Well, let me get my little drawery thing. Carbon hydrogen is definitely non-polar. Otherwise, organic chemistry would be very different. But the carbon-chlorine bond is a little bit polar. So we do have 2 bond dipoles in there. But due to the symmetry of the molecule, which obviously I've drawn the Lewis structure and it looks like it's a square planar. But of course, we know Lewis structures just simplified and don't actually show shape. So if I went ahead and used VSEPR and worked out the steric number as 4 bonds around the carbon, that would of course be a tetrahedral shape. Either way, due to symmetry, those bond dipoles would cancel each other out. So we can see dipole-dipole interactions between neighboring dichloromethanes, like over short range, etc. However, that dipole does not meet our criterion for hydrogen bonding, right? So of course our chlorine end of the one would be our delta minus, our carbon end would be our delta plus. So we do have polarity there. We can have dipole-dipole interactions, but not hydrogen bonding, because we don't have that. Chlorine is neither an oxygen, a nitrogen, or a fluorine. Where's my checky check? So that would be a nope. Okay, what about between this compound and molecules of water? Again, okay, don't get confused. You can still have a dipole-dipole interaction with the water molecule, because obviously water has a dipole. So like the delta minus end, the oxygen end, is not going to be interacting with the chlorine, but the delta plus end, the hydrogen, you can visualize quite easily that delta plus can have a dipole-dipole interaction. Sorry, I drew that quite far away, with the chlorine end of those bond dipoles, but that is dipole-dipole, not hydrogen bonding, because it doesn't involve nitrogen, oxygen, or fluorine on the dichloromethane. So that is a nope. Okay, so our last one is our dimethyl ether, which has kindly been drawn for us again. Thank you. So we can see that we have some polarity here, right? So carbon-oxygen bond we would expect to be polar, right? The delta minus would be the oxygen in the middle. The delta plus would be on each carbon. Now, again, in the molecule as a whole, that is highly symmetrical and cancels out on average, right? But that doesn't mean that you can't have some dipole-dipole interactions between dimethyl ether, depending on what it's mixed with, right? In the particular structural type of dimethyl ether, you can see because that oxygen's in the middle there, and looking at the shape of dimethyl ether, I wouldn't even really expect dipole-dipole interactions between if you just had pure dimethyl ether, just because this carbon hydrogen and the shape of the molecule, carbon hydrogen is non-polar. So I can't see an easy way, like geometrically, for the carbon oxygen dipole to actually get close enough and interact with another carbon-oxygen dipole on a neighboring dimethyl ether. But either way, definitely no hydrogen bonding interactions because we don't have an oxygen, nitrogen, or fluorine there. So that'd be a no. Okay, so we've established dimethyl ether does have a dipole moment between the oxygen and carbon. So those are polar bonds, but it cannot form hydrogen bonds with itself. A, because that's not an oxygen hydrogen, nitrogen hydrogen or fluorine hydrogen bond. B, because the shape of the molecule. Anyway, it'd be very hard for even the dipole-dipole interaction to occur between dimethyl ether molecules. But just because something can't form hydrogen bonds with itself doesn't mean that it can't form hydrogen bonds with water. So if we look at the water molecule that I conveniently drew earlier, we can see that we have our delta plus hydrogen end and our delta minus oxygen end here. So it is not inconceivable at all that there could be an interaction between this hydrogen here, and I know it's a long way away, and the polar oxygen here. Okay, so we've got a delta minus on this oxygen here, delta plus here. So the question is that just a dipole-dipole interaction, or is it a hydrogen bonding interaction? So if we look back at our criteria for hydrogen bonding, the interaction has to be between an oxygen hydrogen bond, so highly polar, with an oxygen nitrogen or hydrogen on a neighboring molecule, which is very electronegative and has at least one lone pair. So dimethyl ether is actually fulfilling this criteria for forming hydrogen bonds with water. So even though it cannot hydrogen bond with itself, it can form hydrogen bonds with water. Okay, so I think that's the 3 different flavors that you could get for this kind of question. So hopefully that is enough to help you on your way.